Thank you all for coming back for the IEA Task 44 talks series. Today, our speaker in the renewed series, our first speaker, is Marcus Becker of TU Delft. And he'll be presenting on closed-loop model predictive wind farm flow control under time varying inflow using Floridine. So take it away, Marcus.
Thanks for the introduction, Paul. I'm quickly going to share my screen. And now you should all see my presentation. So, yeah. So my talk today is indeed going to be on closed-loop wind farm control. In particular, we've used the dynamic parametric model Floridine in order to achieve that. And it's not necessarily established practice on how you should or could do that. So I'm going to take you through a couple of different ways to approach this problem and the results coming out of that. Oh yeah, before I start, I'd also like to acknowledge my collaborators. The work done here is based on a couple of different papers. So first of all, Jan-Willem van Wingenden, my professor, Dries Allers, my co-promoter, then Maarten van den Broek, Maxime Lejeune, Raphaël Moederfort, who's contributed on the Flora side, and Philippe Châtelain. So part one, let's start with the problem statement. What are we trying to achieve, and why would it make sense to use a dynamic model for that? The goal overall that we've looked at is AP maximization, so annual energy produced. And typically how that's approached is that we take the wind rows, so historical data, we bin that into wind directions, wind speeds, turbulence intensities, so some ambient conditions. And then coming from there, we pick out each bin. So one bin might be 9 meters per second at a certain wind direction and TI. And then we simulate those in a steady state model. Now we have two ways of doing that. We can use that in a baseline way where the turbines are just greedily optimized, so to say, aligned with the wind direction. Or we try to do something fancy wind farm flow control type. And one of those options would be wake steering, but could also be helix control, for instance. Coming from that, we do get the baseline AEP and estimate, and we do get an AEP estimate if we would do yaw steering. And as a byproduct, we also do get a lookup table. So what does the lookup table consist of? Well, the lookup table just takes the bins that we fed in and tells us how the turbine should behave in these conditions. And then during application, we would find out, okay, currently we're facing these ambient conditions. And from there, we look up in the table how our turbines should align themselves, for instance, with the wind direction in order to maximize the power generated. And therefore, we have this term power maximization. The issue arises as the wind rows doesn't necessarily represent what's actually happening in the field, in a sense that in the field we have a time marching event chain, so we have states that change. We don't necessarily jump from one bin to the other, but we transition between them. And thereby the wind row is an approximation of what's happening. And taking these dynamics into account might yield a different wake description and a different way of looking at the problem than the steady state option. So this has sparked the interest and development of several dynamic models, which move from the steady state, the Gaussian model, wake model, and Flora's toolboxes, or the PyWake toolbox offers, back to a more dynamic description. And one of those wake models is called Floridine, the flow redirection and induction dynamics model, initially proposed by Pieter Gebraat, and then reworked by myself and a couple of other people. And the basic idea is that we experience states at the rotor plane, like the turbine states. This could be yaw angle, for instance, or the actual induction. But it also contains wind directions, wind speeds, and wake states in general. And then we propagate these downstream. And as they propagate downstream, they have their delayed impact on the downstream turbines. If we apply this then in a wind farm, then we might get a simulation, as you can see on the right-hand side. So our wind turbines are experiencing some sort of control and changes in the flow field. And then thereby the wakes do change and start interacting with the downstream turbines, but in a delayed manner. And I think that's the main part. What these models can offer over steady states is the delayed dynamics, but also not that much more. So if we compare this to LES data, then we see in the light blue background data, we see the turbulent LES data. For a single turbine in a 10-turbine wind farm, you can see the case on the top right. And the wind direction is coming from from south, so to say. So from down going upwards. So we have this one turbine that is really affected by a lot of upstream turbines. And then we see in the light blue the LES with all the turbulent effects, such as wake meandering, for instance. And then we see in the dark color, the low-pass filtered version, in order to get a better idea of the trend, what's captured by the LES data. And then we have the steady-state model in blue, and in orange we have the Floridine model, a particular implementation. But what we see is that the steady-state model seems to be slightly out of phase with the low-pass filtered data, and that the Floridine model is able to capture these dynamics again. But it's also clear that we're not capturing the entire dynamics present in the LES. There's a lot of effects that we cannot capture. It just gives us a better dynamic trend of what's happening in the flow field. So how could we apply this in a closed loop manner? Here's the closed loop design that we've envisioned from the start. In the center top, you see the high fidelity simulation environment, which is replacing the wind farm, as we don't have a wind farm accessible. And from there, we get some sort of measurements. It can be that we have the rotational speed, the blade pitch, etc. But we somehow need to convert that into something that is meaningful to the wake model. And then we use those measurements in order to estimate the state of our dynamic model. In our case, we're using an ensemble Kalman filter for that. And then we take this estimated state and we give it to the controller. What the controller is then doing is taking this dynamic model with its estimated state and propagates it into the future and tries to find the best control actions that this model can take in order to maximize a cost function, and then provides the control inputs to the real wind farm. And then the cycle continues. But this controller part hasn't, or there are some ideas how we could do this control part, and we'll look into how we focused on it next. So part 2 is going to be about the control, and we'll start off with the basics about model predictive control, what it means, and what the receding horizon problem is that we're focusing on. The receding horizon problem, as sketched out here, is looking at 2 turbines. And with these 2 turbines, we have our control input shown in blue, so the yaw angle of the 2 turbines, turbine 1, turbine 2, and the power generated as equivalent. And what we would like to see is that our first turbine is misaligning itself, thereby sacrificing some of its efficiency. But the second turbine, as a result of this redirection, which comes from the misalignment, starts to produce significantly more power. And the optimization problem, of course, then is to find the alignment angles of the 2 turbines in order to maximize, well, maximize what? So in the steady state case, we would say we maximize the power. So we would only look at the end of the horizon, would look, okay, what is the best way we can achieve such that the power from turbine 1 is the maximum and the power from turbine 2 is the maximum. Well, the farm power is the maximum, so to say. And then the power of turbine 1 and turbine 2 is imbalanced such that the farm power is the maximum. But for a dynamic description, a time marching description, we actually trying to maximize the energy produced. So the difference is that we're integrating over time from the current time step up until a prediction horizon. So we need to say, when is our prediction window over? Do we have the next minute in order to generate the most energy, the next 10 minutes, the next hour? That is a question that you need to answer in this context. Then next to the prediction horizon, we also do have an action horizon. The action horizon is meant as something where we can take a control action. And the effect of that control action is then felt as part of the cost function in the prediction horizon. We then also have an update time step, TU, which means that we're optimizing our control actions for this entire prediction horizon. But as we know, things will change. So wind directions change, wind speeds change, etc. And therefore, we're only taking small steps. So we're then pushing our receding horizon problem one step further. We're applying this first step of the optimized yaw trajectory that we found, and then we're redoing the entire optimization. That is the basic setup for a receding horizon control problem. And in part two, I'd like to talk about some research that we did on time-shifted cost functions. And this has been published along with the CCTA conference this summer. And it's about trying to play with this time dynamics. And what I mean by that will become a bit clearer now. So we have the first turbine, we have the second turbine established, and the yaw angle of the first turbine changes, but with a delay, the second turbine feels that approach, this benefit. So in our optimization problem, we might think, okay, the yaw angle of the second turbine especially has no impact on, or has little to no impact on the overall cost function. So why should we make it part of our optimization problem? If we look at the previous design, the yaw angle of turbine 2 has no effect on the power generated by turbine 1. Therefore, we only take the power generated by turbine 2, or the energy actually, as a cost function for the yaw angle of turbine 2. This creates then a cost function as formulated down here, which is then to be maximized, which is the cost function with respect to the optimization parameter of yaw angle turbine 2 equals the energy produced by turbine 2 over the action horizon. Also, action horizon, as the yaw angle of turbine 2 has an immediate effect on the power generated by turbine 2. So there is also no need to simulate the entire prediction horizon. In contrast, turbine 1 or the yaw angle of turbine 1 does have an effect of the power of turbine 2. So we have this immediate effect on the power generated by itself, but we also have this delayed effect. And the idea then was to, assuming that we know this delay time from one turbine to the other, that we start synchronizing the two. So that instead of just integrating over the entire prediction horizon, we integrate over this first time interval where gamma T1 impacts P T1. And then with this time delay that we assume that we know, we also integrate over the power generated by turbine 2. This creates two optimization problems, the optimization problem of turbine 2 and turbine 1. And the optimization problem of turbine T1 depends on the result of the optimization of turbine T2. As in order to simulate the conditions of turbine 2, we need to have the yaw angle of turbine 2. So first, we need to solve the optimization problem to the left, and then the optimization problem to the right. And if you have a longer chain, you can imagine that we are essentially marching backwards. So we're marching from the most downstream turbine to the most upstream turbine. The most downstream turbine intuitively can only do things in order to save itself. And the most upstream turbine is doing something that will over time affect all the downstream turbines. A second part to this optimization problem is to start breaking the problem into smaller pieces and to segment our farms. This is something that isn't uncommon in the optimization for wind farm flow control. But what we can do now here as well, since we've chosen this time-shifted approach, is that we can split the wind farm in time. So in order to showcase that is that we have this first optimization problem, which just actuates turbine T2, and it only measures at turbine T2. And it's only been simulated for the action horizon duration. So we have a much shorter simulation, and we have less optimization problems, less optimization variables that we need to find. In contrast to that, we also do have the second optimization problem, which then has to simulate until the effect has propagated to the second turbine, but also not much longer because the integral doesn't go much longer. And thereby we also have a shorter time horizon there. And we have this two-part, as I also talked about earlier. We have the first optimization problem, and then we have the second optimization problem. Then the second split is in space, which is the more common approach, which is that we just assume turbines that don't affect or are not in close proximity don't affect one another. So the turbine on the top left, for instance, show that here maybe. So the turbine here is not assumed to have an effect on the turbines here, for instance. I've now quite aggressively split this wind farm just in order to drive the point home. If we then look at our optimization schedule, so the optimization problems that we need to solve, then it might look something like this. So we have the dependent optimization problems in one group of turbines that affect one another. So in this case, turbine 5, 4, 3, and 1 might depend on one another. So they need to be simulated together. And then within this row of turbines, we're just marching from the backmost turbine to the frontmost turbine. And then we have these different groups split. So we have actually a lot of, instead of one big optimization problem where we need to find the yaw angles of all turbines at the same time using one cost function, we have a lot of small optimization problems, which are reduced in complexity and thereby hopefully easier to solve. Which brings us to the next topic. How does this, at least mathematically, scale or help us with the complexity of the optimization problem? And to this end, I've segregated 4 parts of the complexity. So in yellow, we have the number of simulations. In green, we have the number of turbines. In orange, we have the time steps that need to be simulated. And then in blue, we have the number of optimization variables per optimization problem. And the proposed time-shifted approach drives the number of simulations up, as mentioned earlier. However, per simulation, on average, it brings the number of turbines down. It reduces the number of time steps that we need to simulate, and it also strongly decreases the number of optimization variables that we need to focus on. So we can calculate a bit the ratio between the one option where we have a lot of optimization variables and a lot of time steps and turbines, but only one simulation, and the other version, and take these results with a grain of salt, because this strongly depends on the implementation, on the algorithms that you have, etc., and how much time you give it to converge. But for a test scenario of 10 turbines with 35 degrees of freedom per turbine, so 35 time steps for our action horizon, and 125 time steps for the baseline, we see, depending on the optimization cost, if it's linear, quadratic, or exponential, quite big reductions in computational effort. This might not necessarily mean that your optimization algorithm runs shorter. In our experience, it just converges faster. So we need less time in order to achieve the same or a better quality of a result. So in part 3, we're going to put this algorithm to the test. And this is the first time that we're essentially displaying the entire closed loop framework. So we have on the top right the true wind farm simulated in SOFA, in our case with the 10 turbines simulated as actuator disks. And from each turbine individually, we receive power and wind direction measurements, which we assume to be available. So power, I think, is clear, but wind direction measurements, we haven't modeled really a wind vane or something alike, but we have more taken probe measurements at the location of the turbines, or just assumed that we have clean measurements. And then we feed those into a state estimation, so the ensemble Kalman filter, as I mentioned earlier. And then we bring that state to our optimization controller, which maximizes the energy over time. We do not use preview here. Preview meaning we don't have knowledge of wind direction changes that might be ahead, simply as we don't deem it to be that realistic at the moment, but we'll talk about that later. And yeah, maybe also to put a note on how we solve it, we have a particle optimizer. So we have different particles that solve the entire plane, assuming a non-convex optimization problem. And we run a lot of Floridine simulations in parallel in order to assess what's the ideal yaw angle. Now, we can now test different settings against one another, which we'll also do. But of course, it's also interesting to look at the lookup table controller. So in our lookup table controller setup or our steady state problem, instead of energy maximization, we're maximizing power. We try to have a bit of a bare bones default version of this controller, which has the same degrees of freedom, so also plus minus 30 degrees. We use serial refine, and we provide a 2-degree deadband controller that essentially just updates the lookup table or the yaw settings based on the lookup table if the wind direction changes more than plus minus 2 degrees. And also this controller doesn't have access to preview. One essential difference to the closed loop MPC controller is that in this case, we directly feed in noise-free wind direction and wind speed data. So this controller has access to perfect measurement, so to say. And then the controller applies the turbine orientation to the true wind farm. Our simulation case is a 10 turbine wind farm, as said before, and we'll here showcase just a 10-degree wind direction change first in order to structurally compare the different approaches that the controllers have to this optimization problem. The ambient conditions are 8 meters per second at roughly 6% TI, and the entire simulation duration is about 40 minutes. So in order to understand how the controllers are making their decisions, we'll first look at the yaw angles imposed throughout the simulation by different turbines. So one of the most dominant turbines here is turbine T0, because it's affecting this entire row. And turbine T0 is shown here. Its orientation is shown with a baseline orientation, which is given in this striped line. And then the continuous line is the wind direction. So we see our baseline is changing the orientation of the turbine during this wind direction change, which happens from 1,000 seconds to 1,600. And then afterwards, we have steady state conditions, and initially we have steady state conditions. On the left side, we also have this striped vertical line, which indicates the moment that the turbines start yawing or the controller engages. We then first plot a controller with a short prediction horizon. And this controller is just maximizing the energy over this given prediction horizon. So this controller is really calculating the integral over the given time, as opposed to taking this time-shifted approach. The time-shifted approach comes then later with the blue lines. So this is the basis version of the cost function. And we see that with the short prediction horizon, our turbine engages into yaw steering, initially at quite low levels, so 5 degrees-ish. Then during the wind direction change, there's quite some change before it then settles for its new orientation. If we elongate the prediction horizon, we do get much more aggressive yaw steering. So our turbine changes its orientation at a later point in time, curiously, which we assess to be due to no convergence yet, or not ideal convergence yet. But it goes to a much higher yaw angle in order to benefit the downstream turbines, as it has more time to see the benefits of the yaw angle that the first turbine imposes. Then it goes through a similar transition. It takes longer time, of course, to switch from this high yaw angle to the other side, so to say, of the row orientation, and then it finds sort of its new steady state condition. Now we have the time-shifted approach. The time-shifted approach immediately goes for the aggressive yaw angles, and then goes at an even later point and switches to the new direction. So it stays a bit longer on the upper side of the wind direction and then switches to the lower side. But it finds a similar equilibrium afterwards. Then as next candidate, we have the time-shifted approach with linear preview. So linear preview is an imperfect version of preview, but let's just assume it just knows what the wind direction change is coming. And then we see that the linear preview actually goes at an earlier stage and changes its orientation, very much opposed to what the time-shifted approach does with what the time-shifted approach does without linear preview. And lastly, we've added the lookup table with 2 degrees. And then we see that the lookup table also immediately changes its yaw angle, but goes to an even more extreme yaw angle than all of the closed-loop controllers that maximized energy. We can also look at the second turbine just to have a quick comparison. This turbine is interesting as it starts to interact with this far downstream turbine. So if you can see that here, we have this turbine T2, and it wakes down here, turbine 9, I believe. And depending on the prediction horizon that you have, so on this one hand side, we have the 350 prediction horizon. That controller doesn't even start to do yaw steering, whereas the controllers that either do the time shift or have a longer prediction horizons, they do start doing yaw steerings, equivalent to the lookup table. So that means that we are able to predict with this model that this far wake interactions are still worth it, something that other models like the free vortex model methods have issues with due to numerical instabilities. But how does it compare in the energy generated? First, we compare the closed loop controllers because they really have the same conditions. And there we see that the short prediction horizon leads to the lowest gain, so below 1% initially. Then we see a dip due to the wind direction change. So the controller needs to change the wake steering from one side to the other, but it very quickly recovers and then starts going above 2 to 4%. Also notable, we're now looking at the energy generated over 10 minutes. So we have an integration window of 10 minutes. That's why it goes up and down, not over the entire time. Then if we go for the longer time horizon, we do see that in this initial phase, the controller is able to maximize much more power, but it also suffers more due to its choice of extreme yaw angles, and then starts to recover again after the wind direction change. So it gains more in the steady state condition, but it also suffers more. And this is consistent for the time-shifted approach, but also for the long prediction horizon. Lastly, among these controllers, we have the one with linear preview, which is the only one that manages to avoid falling below the baseline, because it starts changing its yaw angles early enough in order to anticipate the wind direction change. So this really shows that we can reformulate our optimization problem, but without preview, it's really hard to not run into these conditions where we've committed to large yaw angles, and then a sudden wind direction change can really hurt us, from which we need to recover in opposite to the baseline. And then the slightly frustrating result for myself is that the lookup table easily outperforms the closed loop control approaches by even going outside of the initial bounds of this figure. But it also has the steepest loss during the wind direction change. It's the last one to start recovering again, and then slowly it comes up again to this new steady state where the time-shifted approach already is, but it also starts outperforming the 1,000-second prediction horizon. And I think this is a bit the starting point for a deeper analysis that we're still working on, where it's not that simple to close the books now and say like, oh, lookup table is just better, let's go home, because it's this question, at what cost? And we've initially seen that the lookup table controller that we chose, of course not for all lookup table controllers, is tending to quite aggressive yaw angles, whereas the closed loop control, due to the fact that it's maximizing energy instead of power, is going for, by design, more conservative yaw angles. Also, the lookup table has access to ideal information in this case. So it has no noise, it doesn't have to deal with the conversion of power to wind speed, etc. So it just has ideal conditions. I think that's worth mentioning here. So, but we'll draw some first conclusions regarding the dynamic model predictive control first. As I said, maximizing for energy yields more conservative misalignment angles for shorter durations than for long ones. That's just to say, if your prediction horizon is longer, your optimization problem will go for more aggressive yaw angles than if your prediction horizon is short. The dynamic optimization problem can be reformulated to neglect the inter-turbine delays, which makes it similar to the steady state one. This was the time-shifted approach, where we said, okay, if we take away these delays, then we also do see these much more aggressive yaw angles, even without the cost of simulating longer time horizons, and that larger yaw angles come with greater gains, but also with greater sensitivity to wind direction changes. I think that is clear from the results. We can also draw some first conclusions from the dynamic model predictive control in comparison to the steady state lookup table. First, as I mentioned, the comparison is difficult. The steady state lookup table needs to be applied dynamically. So we're, roughly speaking, it's off design conditions, so to say, but it's also not the optimization that it's been optimized for, so to say. It requires some sort of state estimation and measurement strategy, which we haven't implemented. We've just supplied it with the ideal values because we don't have, or at least in our research, it showed that there's no really established way of doing this. And it does not follow the same cost function. So maximizing power is something else than maximizing energy. The steady state lookup table controllers returns more optimistic yaw angles by design. As I mentioned, maximizing power means that we're going for aggressive yaw angles, but that can hurt us if a wind direction change is coming, or if our environmental conditions are changing and hurting the steady state assumption. This is possibly limited by uncertainty. What I mean by that is that you do have the choice to apply uncertainty during the lookup table creation, which we didn't do in this case. And then you also do get less aggressive yaw angles. And a last thing that I only briefly touched upon is that lookup tables have the advantage of converged set points. And what I mean by that is that a model predictive controller has to optimize given a certain time frame or a certain optimization budget. And while we're creating lookup tables, we're not bound by these limits. And thereby we can count on converged set points, whereas the MPC might need more time to converge to a better solution. With this being said, I'd like to leave you with some last, in my opinion, nice visualizations and a statement which we can gladly discuss, which is that wake steering is calculated gambling. So it's gambling in the sense that we're investing, or maybe you should call it more investing, into a certain wind direction and the interaction of turbines. And if your environment changes, then you might not get the return that you hope for. In order to showcase this, I've plotted a case here. So these are two flow fields that are extracted from one another. Blue means that the flow field wind speed is lower due to the wake steering, and red means that it's higher. So what we want is that the downstream turbine is in the red, and the upstream turbine is probably producing a bit less power, but producing this red area that then hitting the downstream turbine. To explain the legend of the turbines, we have this black bar, which is showing how much power this turbine is generating. And then there is an arrow which indicates how much the same turbine is producing in the baseline configuration. Next to that, we also do have the yaw alignment. And I want. So here, we don't see that much yet. Just trying to get this. Okay. So let's go back here. So here we have the wind direction going from the lower left to the upper right. And the upstream turbine is now engaging into yaw steering, causing a higher wind speed area and a low wind speed area. And then hoping, or this is what our strategy imposes, or the lookup table imposes, that the red area will hit the downstream turbine. Oof. I'm sorry, this isn't going as smooth as I wanted it to. And this partially happens here. So now this red area is hitting the downstream turbine, but as we progress, we see that the wind direction has changed further. So the upstream turbine has in the meantime switched its yaw angle to the other side and has created an opposite side of blue and red area. And now the blue area hits the downstream turbine, which causes a loss of energy at the downstream turbine, while the upstream turbine has invested thinking that the downstream turbine might return on that investment. And as we let the simulation play out, we see these events happening more often. So sometimes it works out, so wake steering works, but it also sometimes doesn't return the investment that we hope for. This entire simulation is, or these two turbines are just a subset of the entire simulation, so I wanted to show you the entire thing. For you on the right side is the efficiency of the wind farm power. Then in the middle is the efficiency of the wind farm energy integrated over the last 10 minutes. And then in the lowest one, you have the current wind direction. With that, enjoy. And this is a case where wake steering doesn't really work well, which I tried to use in order to highlight this case, that wake steering doesn't necessarily return the investment that you hope for. And I think something that characterizes this case and makes it tricky for the lookup table yaw steering controller, but also the closed loop controller that doesn't perform much better, is just the fact that we have these long distances between the rows of turbines. and that we, in the meantime, also have these fluctuations of the wind directions, which makes it tricky. As long as we have these densely spaced rows, wake steering does become much more profitable. But we also do see that, for instance, in the efficiency of the energy, we're still below the baseline. We're now 2% below the baseline over the past 10 minutes. And the baseline hasn't invested into misalignment. Just now, for instance, we're going much above, which makes it tricky. But I don't want to leave you on a negative note. So I've done another simulation where it's actually working out quite well. Yeah. So here we have the same wind farm, just in a different initial wind direction. And we do see that initially from the get-go, we're 4% in the plus using wake steering, which is mainly coming from the lower right half side, whereas there's also some far wake interaction on the left-hand side. Now, as the wind direction starts to shift at some point, we do see that the left-hand side gets more engaged, which then leads to quite large gains. So here we see this long row getting engaged and then getting 5% efficiency more on a 10-minute basis. Yeah. Yeah. And with that, since we're in the IEA task, and this is also meant to connect people from industry, I'd like to open up a bit the discussion. What we are working on is a more complete study focused on closed loop wind farm flow control using MPC. That is on its way. But I feel like maybe it would be nice to have a more established way of applying lookup tables dynamically, something like the turbine control community has with Roscoe. And I feel also like we need a better understanding and case studies of realistic flow conditions at a wind farm scale. And by that, I mean wind direction changes, wind speed changes, diurnal cycles, these kind of things, which at the moment, there's a lot of two-turbine results. And I feel like for these dynamic models, it would be more interesting to look at these realistic conditions. And therefore, I open the floor for discussions. Here's a list of the publications related to the presented work from my side, but also some of the tools that we've used to achieve these results. Thanks for your attention.
Thank you, Mark.